afternoon, good morning, good evening. Thank you for joining us for our new virtual faculty lecture series, Through the Lens. My name is Joshua Stewart. I'm the Senior Associate Director for UVA Clubs Global Network, which is our off-grounds regional clubs that help bring programming and events to you all to connect local who's. Through the Lens is a virtual faculty lecture series highlighting faculty from across grounds whose research and knowledge helps promote intellectual discourse. And being away from grounds, you have less opportunities to learn like our current who's. So we're going to bring the professors to you. And this afternoon, I have the pleasure of introducing Professor Kathleen Schiro. She is an assistant professor in the Department of Environmental Sciences at the University of Virginia. She earned her PhD in Atmospheric and Oceanic Sciences at the University of California, Los Angeles. And she was a postdoctoral fellow at the Jet Propulsion Laboratory before joining UVA faculty in 2020. Her research uses field campaign data, satellite observations, regional convection permitting models, and global Earth system models to improve our understanding of clouds, convection, and precipitation in a changing climate. Today's talk will focus on how do thunderstorms grow? How do clouds change as we warm the planet? And join us and join me in welcoming Professor Kathleen Schiro.
Thank you so much, Josh. Thank you. It really is my pleasure to be here. I am thrilled that many of you are joining from, I don't even know where in the world, but greetings from Charlottesville. It's a lovely day here. It is not convecting yet and not raining. So it's really my honor to be with you today. So I'll tell you a little bit about my lab group, how we study clouds, rain, and climate change, and how improving our understanding of thunderstorms and clouds can improve predictions of the magnitude of global warming and associated increases in extreme weather events. I cannot begin without thanking and acknowledging everyone in my lab group. The graduate students and postdocs are shown here, and many collaborators as well. I can't possibly list all their names, and various places that are funding this research. We really have a vibrant group of students and postdocs in our group and in our department that really are behind a lot of this work that we're doing. Right. So what is happening in the climate system? We can start there. So greenhouse gases are increasing. In the top right, we see that there's an increase in carbon dioxide that's measured. This is from an observatory at Mauna Loa in Hawaii. There are steady increases in carbon dioxide concentrations that have been observed since the late 1950s. And that is projected to continue with future emissions of greenhouse gases. Now, these rates are rather unprecedented. So this is just taken from a recent climate report. You can see that what we call paleoclimate proxies, or taking information from, for instance, ice cores, reconstructing the carbon dioxide concentrations, reading the carbon dioxide bubbles in those ice cores, can tell us something about the past. And so comparing what we have today in terms of global concentration of carbon dioxide versus what had been many thousands of years ago, we have really unprecedented rates of carbon dioxide and other greenhouse gases in the atmosphere. So these emissions from greenhouse gases are responsible right now for approximately 1.1 degrees Celsius of warming since a pre-industrial baseline period of 1850 to 1900. And then averaged over the next 20 years or so, global temperature is expected to reach or exceed 1.5 degrees Celsius of warming. Now, these are the types of temperatures where we're going to, and we already see significant changes to things like extreme weather events. And so there's a way that we attribute that and look at those. And this is really what has motivated a lot of my work, is to try and better understand extremes. So in terms of attribution and thinking about the climate system in terms of the warming that's occurring. So first of all, the human influence has warmed the climate at a rate that is completely unprecedented in at least the last 2,000 years. So that's what's shown in the left here. So these are reconstructions of temperature from paleoclimate records, and then the observed temperature towards the end of this curve. And we're kind of approaching values of warming that are sort of warmest in a multi-century period that's beyond what we've seen in even the last 100,000 years. So this is really unprecedented warming. How do we know that humans are causing this warming through the increase in greenhouse gases? Well, we run climate model simulations, so things that simulate the atmosphere, the ocean, the interaction of those two with the land surface, and we can input different forcings into the climate models. So for instance, if we try and recreate the observational record in black here with climate models, we can only really do that if we input into the climate models that there has been an increase in greenhouse gases. So in other words, you have to simulate human and natural forcing in order to see the increase in temperatures that we've observed. If you don't do that and you just simulate natural forcing, like just solar and volcanic forcing, you cannot reconstruct what we've observed in the last few decades. So that's how we attribute climate change to humans. That's one line of evidence. There are multiple lines of evidence from paleoclimate, process understanding, observations, as well as these global and regional climate simulations. So a lot of this is summarized in a number of reports now that have been put on by the United Nations, the Intergovernmental Panel on Climate Change. The last report was in 2021 and 2022. I will be sampling from the Working Group 1 aspect of this report. This is the physical science basis of the IPCC reports. So really talking about physical changes to the climate system. There are other parts of the report that talk about adaptation, mitigation, but I'm going to be focused, I'm a physical climate scientist, so I work on the physics of climate and climate change. But this is a really, if you haven't heard about this, I encourage you to go take a look at these resources. These are incredibly large efforts. These are hundreds of authors from tens of countries, over 14,000 cited references, and the public also can comment on them. And the government can comment on them. Governments can comment on them. In this latest report, there were 78,007 expert review comments, and all of them have to be addressed. So this is a really monumental effort, and this happens about every 5 years. Okay, so extreme weather. I mentioned that, the climate is changing and we're already seeing some of those changes, and some of those are in the form of extremes. So what is an extreme weather event? So an extreme weather event is defined by the IPCC as an event that is rare at a particular place and time of year. And changes in extremes can be examined from two perspectives. We either focus on changes in the frequency of given extremes or on their changes in intensity, and that's kind of how we quantify them. So wildfires, hurricanes. And when we think about how much confidence we have in attributing extreme event changes to climate change and increases in greenhouse gases, our confidence level sort of depends on a couple of things. So first, it depends on the quality of the observational record. So we don't always have good observations of the processes we're trying to look at. And the lack of quality of observations of certain processes, that impedes us in terms of process understanding. So the things that we have better observations of, traditionally speaking, we have better understanding of those physical processes, or at least a way of more definitively approaching the problem. We also can use models, and we can use statistically based models, physical based models, depending on what the problem is. I use physically based models in my lab group. And the ability of models to simulate a given type of extreme event is also something that depends on, like, our confidence in whether or not we can project future extremes depends on how well we can simulate those realistically in a physical model. So here's sort of a spectrum of things that we are more or less confident in, depending on these three sort of like pillars of scientific knowledge. So in the top right here, these are things like extreme heat and extreme cold, or in other words, temperature extremes. And then things down here are things like compound events, like wildfires, that depend on changes to winds and moisture and multiple aspects of the physical climate system. And then you find a collection of extreme precipitation events. And those are we have the least confidence in things like convective storms, which is something I study. And so that motivates a lot of what I'm doing. How do we use observations to better represent them in physically based models when they can't be explicitly represented because they're too small in scale? And how do we use observations in novel ways to try and physically understand them so we can tell the models that can't explicitly represent them how to represent them? So I'll also make a statement that extremes are already more extreme. We have various levels of confidence in those extremes. So I'll just run through, I'm sure a lot of you are quite interested in extremes. I'll run through some basics of what on a global scale the trends are in, for instance, I'll start with heat extremes and cold days. And so there are different terms the IPCC uses and attributes different confidence levels based on, again, these three things I mentioned, the observational record, our ability to simulate things in models, and our process understanding. And so they kind of attribute things into low, medium, and high confidence. And within the high confidence territory, there are different phrases that they use to attribute even further detail the level of confidence we have in certain things. So likely, very likely, extremely likely, or virtually certain. So on the x-axis here is sort of the confidence and attribution of trends in the present day to human-induced climate change. And then on the y-axis here, which more or less goes one-to-one with what's observed, is the confidence and projected changes for global warming and physically based models with some greenhouse gas forcing. So for heat extremes, they're in the top right here. So we have a lot of confidence in that heat extremes are increasing. So, taking this language directly from the IPCC, it's virtually certain that there have been increases in the intensity and duration of heat waves at the global scale. And it's extremely likely that human influence is the main contributor to the observed increase in the intensity and frequency of hot extremes and the observed decrease in the intensity and frequency of cold extremes on a global scale. Then when it comes to drought, warmer temperatures lead to greater evaporation of water from the surface. And so human-induced climate change has contributed to increases in agricultural and ecological droughts in some regions due to evapotranspiration increases. So we have medium confidence in that. And more regions are affected by increases in agricultural and ecological droughts with increasing global warming. So that we have high confidence in. So we've been able to make statements about droughts as well with decent confidence. Compound events, so such as concurrent heat waves and droughts, have become more frequent, and we actually have high confidence in this and how this trend will continue with higher global warming. And then fire weather conditions, so like compound hot, dry, and windy events, have generally become more probable. So we have medium confidence in that, and there is high confidence that they will become more frequent in some regions. As far as TCs, tropical cyclones, it's likely that the global proportion of the higher intensity hurricanes, category 3 and 5 storms, has increased over the past 4 decades. And that attributing that to climate change, and that TC translation speed has likely slowed. So what does that mean and why is that important? Well, if a tropical cyclone is slowing as it hits the land surface, it's going to dump more rain on land and has a greater likelihood of flooding. So translation speed is really, really an important aspect of the potential impact of tropical cyclones. The global frequency of TC rapid intensification events has likely increased over the past 4 decades, but actually the total global frequency of TCs will decrease or remain unchanged with increasing global warming. So the more intense systems will become more intense, but actually they're not necessarily increasing. The total number of storms is not necessarily increasing in frequency. And now we're getting more to my realm of things in terms of thinking generally about heavy precipitation. So the frequency and intensity of heavy precipitation, they've likely increased at the global scale over a majority of land regions with good observational coverage. Most of the observed intensity of heavy precipitation over land regions is likely due to human influence. And there is low confidence in past trends and characteristics of severe convective storms, such as hail and severe winds, beyond an increase in rain rates. So we have some confidence that we have increased rain rates over land regions and over much of the globe, but there is low confidence in severe convective events. So more motivation for, why am I doing what I'm doing and what motivates me in my work? So really improving the prediction of heavy precipitation, heavy convective precipitation or thunderstorms, though I put that in quotes because not all deep convection produces thunderstorms, and precipitation extremes in present and future climate is really what I'm motivated to do. And I approach this in sort of a multifaceted way, but my approach is to study which environments support the growth and maturation of thunderstorms so that we can model these events more realistically. So trying to learn from observations or the models themselves in terms of how these convective systems mature so that we can build statistical models to try and represent them in more physically based complex models. And another thing that my lab group does is try and constrain our uncertainty in the magnitude of global warming from anthropogenic greenhouse gas emissions. So how do we do that? Well, I'll explain to you in a little bit that cloud changes actually create a significant spread among climate models and their warming responses to greenhouse gas increases. And so what we try and do in our lab group is study how the cloud landscape is changing and how that modifies the energy balance of the Earth, and try and attribute physically or provide a physical explanation for why certain cloud types are changing in the ways that they are, and which changes to cloud types are most impactful in terms of changes to the energy budget of the Earth. Okay, so I'll start by talking about my first approach and trying to understand thunderstorms and what our group has generally been up to. A few definitions. So convection, I'll talk about convection a lot. It's the movement caused within a fluid by the tendency of hotter, less dense material to rise and colder, denser material to sink under the influence of gravity, which consequently results in the transfer of heat. I'm going to be talking about atmospheric moist convection, picture to the right. And I'm going to be primarily focused on deep convection. So convection that reaches the depths of the lower atmosphere and goes up to, depending on where you are on Earth, tens of kilometers, 10, 15 kilometers, and produces heavy precipitation. Okay, so there are three key ingredients required to initiate convection. The first is instability. So what is instability? Well, let's talk basic physics. So we have an unstable equilibrium. You can think of a ball that's rolling off of a hill. And if it's unstable, which it would be if it were a ball on top of a hill, it would be running away down the hill. And then once you get down the hill, if you were to push the ball up the hill, it would fall right back down the hill. So that's what we consider stable and unstable equilibrium. So when we talk about instability, we're talking about sort of a runaway effect of air in the atmosphere running away in the upward direction. Okay, so how do we assess stability in the atmosphere? So this is actually a photo taken. We do this every year in our intro level atmosphere class in the department, where we show the students how we take measurements of the profile of the atmosphere and how we assess stability. So this is my lecture TA, David Crow, who's outside of the front of Clark Hall. This weather balloon, this radiosonde was launched, I think maybe 3 or 4 weeks ago now. And so what it does is it takes readings of temperature, pressure, moisture, and winds, and it returns those back. And so what we can do is we can plot the vertical profiles and use various metrics in our understanding to see whether or not the atmosphere is stable or unstable, or many other things that I won't be talking necessarily about today. So in order to sort of think in theory about air rising and whether or not it would be stable or unstable, it's helpful to kind of think about this theoretical construct called a parcel. So air doesn't necessarily rise in this tight packet and nicely packaged thing called a parcel, but let's sort of assume, just for the sake of simplicity, that it does. So a parcel in this case is an air pocket that's rising that isn't exchanging energy with its surroundings. And as it rises in the atmosphere, it cools and condenses through expansion. The pressure is lower above than it is below. And what we can do is we can sort of assess, okay, if we had a parcel with specific characteristics that are rising in the atmosphere, how does the density of that parcel with those surface characteristics it's carrying with it compare to what we've actually observed and what the air is doing aloft, which the air can do many different things aloft based on if there's air coming in from other places, or what we call advection. So there could be cold air advection, warm air advection, different motion of air aloft, and that can affect the difference between the air that's rising, the density difference between the air that's rising and the surrounding air. And so it's really density differences between the air that is in our parcel and the surrounding air that's going to determine whether or not we're stable or unstable. So if the temperature falls away rapidly with height, so much so that this rising parcel of air is warmer than its surroundings everywhere along its trajectory, warmer, and really what I mean by that is less dense than its surroundings everywhere, then the atmosphere is considered unstable and the air parcel is what we refer to as buoyant, and it'll continue to rise. So there's something else here that I'd like to introduce that isn't necessarily just, we're not talking just about temperature, we're also talking about moisture. So things have a specific amount of moisture that they've acquired from the surface, the parcel is rising with that moisture in it. And what happens is as the air parcel expands and cools, it releases the energy that was latent within the water vapor. So it's cooling and the air is going from a higher energy, the water molecules are going from a higher energy state, which is vapor, to a lower energy state, which is water. And in the process of doing that, it releases latent heat into the parcel or into, the updraft of the convection. And so when it does that, it actually makes the parcel and the air that's rising and convecting less dense, even less dense. And so that helps to aid in creating additional instability in the environment. So the amount of moisture that exists in a parcel and in rising air is really impactful for actually what ends up happening in terms of the development of thunderstorms. So that's sort of depicted on the right here, where if you start with a parcel at the surface and it goes up in the atmosphere, it's going to go up faster if you have more instability. And if you have more instability, or you can have more instability because you have more moisture in your parcel, and that moisture is releasing heat as the parcel is rising. And so that aids in the increase in instability that can occur that would fuel deep convection. Okay, so another point I'd like to make, this is an oversimplified view of convection and deep convection. And one of the ways in which it's oversimplified is, we don't just have a parcel that's rising from the surface and not interacting at all with its environment. It does interact with its environment. It's not a closed system. So how does it interact with its environment? Well, we actually have substantial mixing that occurs between the non-cloudy air on the outside and the cloudy air. And that matters a lot for the instability of the updraft. And so there are kind of two ways I like to think about mixing. One is more turbulent in nature, where you can kind of have little turbulent eddies on the outskirts of your cloud, and that can sort of like nibble off the edge of the cloud if you have dry enough air on the outside. Or you can have more coherent inflow and coherent drafts that are mixing into the updraft that can influence the development of the convection. And so part of what I research is how much mixing occurs between a convective updraft and its environment. What are the characteristics of that mixing? What environmental factors control that? Because it is really impactful for the instability generation. And so just to sort of give a brief, so some of my work has generally suggested that mixing in deep convective updrafts occurs over a pretty deep layer of the lower atmosphere. So it's a little bit counter to how some textbooks try and describe the way that air parcels are rising sort of from the surface, and there isn't any sort of coherent inflow into a convective system that would affect the characteristics of the updraft and its instability. And so some of my work has shown that even for less organized convective systems that you wouldn't necessarily think have a lot of coherent inflow or coherent mixing, that there is a significant amount of mixing occurring in the lower atmosphere. Right. And so what happens when you mix in a lot of air, if the air is drier, you're going to reduce the stability or the instability that is present that would fuel the deep convective updraft. And so that's sort of depicted here, where you have moisture and you have a parcel that's rising and it's not interacting with its surroundings, and it's releasing a lot of latent heat, and it's much less dense than its surroundings, and it really wants to convect. If you introduce drier, cooler air into that parcel, it's going to reduce the instability. And so you might not get as intensive convection and heaviest precipitation. Okay, so we generally in our research group try and understand what contributes most to the instability generation. So this being a really big part of whether convective systems develop or not, especially in the tropics where there isn't much of a dynamical lift, which I'll talk about in a minute, in terms of lifting air and kind of forcing it to convect past a certain point. And so we'd really try and understand how subtle changes in moisture and temperature in the vertical, like by launching radiosondes or using as much as we can publicly available radiosonde data to try and gather insight statistically into what environments support deeper convection. Okay, and how that might change in different regions. So just to give a brief example of some of the conclusions we've drawn so far, like our work, I'm primarily focused in the tropics, but I do some other work in other regions, like in the southeastern US more recently. So our work in the tropics suggests that moisture perturbations in the lower atmosphere, not necessarily like immediately above the surface, but in the 1 to 2 kilometer layer above or even higher up, if you have more moisture in those layers, it's really influential for whether or not convective systems will develop and mature. And that's something that is most probably due to the fact that there's significant mixing occurring in those layers of the atmosphere. And so if you're mixing a lot in, wouldn't it be better if you mixed moister, warmer air into your developing updraft than if you mixed drier, cooler air? And so that's, in some regions, it might be less consequential to have a significant amount of moisture in that layer of the atmosphere, but in the tropics, which is a very large percentage of the Earth, and it's where most of the deep convection occurs, it turns out that the convection is largely driven by moisture perturbations in that above surface layer. Okay, so there's another ingredient that's required for deep convection, and that's some sort of lift. So the lift can be as simple as like directly related to the thermodynamics in the sense that you heat the surface during the day, you create a zone of low pressure. I'm not getting into a ton of details here, but go with me. And then you get surface convergence. And so that surface convergence is, you can kind of think of it as a mechanical lifting, and it helps to push air up that may not lift on its own if it's not thermodynamically unstable. And so another example of this is you have heavy dense air behind a cold front. So you have colder air that's banging up against warmer, lighter air, and that can trigger pretty intense deep convection. We see that in the spring here a lot, where we have low pressure systems that come through, and we have a cold sector of the low that comes down and bangs up against the warm, moist air from the Gulf of Mexico, and along the leading edge of the cold front, you see significant deep convection and a lot of the time. So that's an example of a mechanical lift. I mean, it's not entirely separate from the thermodynamics, of course, because they're all intertwined, but you're providing this strong mechanical lift behind a cold front. Okay, so fun fact, thunderstorms can create their own cold fronts, which can affect their growth. So what do we call those? We call those cold pools. What happens is you have air that is surrounding and interacting with the falling precipitation, and you actually get an evaporation to some extent, not fully, because we see a lot of the rain that does fall. Some of that re-evaporates as it's falling. And when that happens, you're cooling the air. So the air cools, it then becomes more dense in its surroundings, and it'll fall. And when it falls, it also carries other air with it that was higher up in the atmosphere and colder. And so that falls too, it creates a cold pool. That cold pool expands outward. Its leading edge we refer to as a gust front, and its propagation speed and its intensity is determined by its temperature. All determine a couple of things, like how long a convective system might last, or how it might contribute to creating new cells at the leading edge of the gust front. And so these are things that I study in my research group, like how do cold pools affect the life cycle of deep convection? Can we predict statistically the demise of thunderstorms with measured cold pool properties? And then what are those measured cold pool properties? So I mentioned just a moment ago that you can have, for instance, a situation where a cold pool at its leading edge is kicking up warm, moist air, and the surface convergence is encouraging new cells to form. You could also get in a situation where your cold pool intensification and expansion is displacing your unstable air, which is the fuel of your convective system. And so you end up killing your convective system. So in that way, after some period of time, and I don't know under which thresholds, in terms of cold pool intensity or expansion, you would need to get to in order for the convective system to kill itself. But these are the types of statistics we're trying to build with actually in using observational data. This hasn't been readily studied with observations because we don't have very good measurements of convective systems and these sorts of properties, but my group has been doing sort of taking a compositing approach, like taking a number of different data sets and what I think is a really novel approach. One of my students, Sayali, is working heavily on this, where she's using long duration field campaign data over tropical oceans. She's actually using buoys. So buoys record temperature and precipitation, not all as reliably as some others, but trying to string those together and really look at what the temperature looks like with the passage of a convective system and how that relates to the precipitation intensity of that system. And then we've also done something with satellite data where we've identified convective systems through geostationary imagery, just like visible and infrared imagery, and also estimates of precipitation from precipitation radar and microwave instruments, and tracked the individual cells as they're moving in space and time. And then what we've done is we've tried to determine whether or not convective systems are in a growth phase, so like they're horizontally growing, or whether they're decaying. Their precipitation rates are decreasing. They aren't expanding anymore as time is moving forward, things like that. So we can kind of characterize with geostationary satellite data whether or not convective systems are growing, maturing, and decaying. And so that can kind of help us if we're trying to think of a way to relate cold pools and their characteristics to whether a convective system is going to die at some point in the future and what characteristics that would need to have in order for the convective system to die. These sorts of what we call convective tracking databases can be really helpful for that. Here's just a very quick example of sort of a basic plot that she's made that I think actually tells a lot. On the y-axis is air temperature, and on the x-axis is just it's a composite. So these lines are all averages of many different events. And it's a composite from like -5 to 5. This is a time dimension of like 5 hours before and 5 hours after the passage of a convective system over just like a buoy in the tropical West Pacific. And what she's done is she's, like I said, tracked these convective systems and classified whether in their growth or mature or decay phases. And she's composited what the air temperature looks like and how the air temperature changes with the passage of the convective system. So you can see that as a convective system's in its growth phase, it generally is in a warmer environment. So that kind of makes sense to us, of course, because if you have more heat available for instability generation, then you're going to have more intense updrafts. The system might continue growing. And then as you sort of go to mature phase, which is in green, or decay phase convective systems, then not only do you see that like the average air temperature is reduced surrounding these different phases in the convective life cycle, but also something else is happening. You can kind of see, we don't have spatial information as much, but you can kind of see that in time, this like dip in temperature, which is indicative of the cold pool passage, is occurring ahead of the actual event reaching the buoy. So what does that mean? Well, so basically what we're detecting here and what I'm showing is that the cold pool is outrunning the parent convection. And so the cold pool is expanding. What that kind of looks like in satellite imagery is, here, you kind of see that these gust fronts at the leading edge, they're actually kicking up some convection. It's shallow convection. These are like very shallow clouds at the edge of this edge of these cold pools. But then these are the parent convective cells. And so there has to be some, in our head, there has to be some threshold by which like there's some amount of cooling that must occur in the cold pool, and it has maybe there's some threshold for how far outrun it gets, that we can maybe statistically put these pieces together to try and come up with a metric for convective system demise. And maybe that depends on the region we're in, or maybe that depends on other environmental conditions. But these are the types of things that my group is currently thinking about. Right. So one thing that I'd like to distinguish is, I generally study deep convection, and I don't necessarily study what we call severe deep convection, but it's a classification of deep convection. So I primarily focus on the tropics. So I'll explain in a moment, we don't necessarily have severe deep convection, but I did want to define it. So severe thunderstorms are classified as having the potential for damaging winds, tornadoes, or hail. And they're not necessarily classified as severe based on the amount of precipitation that's falling in them. So I mostly focus on precipitation extremes, not necessarily wind or tornadoes or hail. But in many ways, severe deep convection has many classifications and can also fall in the extreme precipitation category. So there's something kind of special going on in the mid-latitudes that doesn't so much happen in the tropics, and that's something called wind shear. So wind shear is the change in wind direction with either height or, change in wind speed with height, or change in wind direction in the horizontal or in height. And so what that can do is that can help to organize convective systems. And oftentimes, for instance, along regions of really intense temperature gradients, you can see that there's significant wind shear. I don't have a ton of time to go into dynamics or anything here of this, but that can help organize and actually rotate convective systems. So that can contribute to, for instance, the development of tornadic supercells and other types of tornadic mesoscale convective systems, which I'll define in a moment. Right. So forecasting deep convection. So what are some of the challenges and opportunities? Well, at operational centers, the skill for both rainfall and severe weather forecasts is really at a minimum in the summer. The reason for that is because we don't necessarily have these clearly defined areas where we have cold air banging up against warm air, and it's sort of a clear zone of convergence where we're going to have some sort of severe weather. In the summertime, it's a little bit more nuanced. The large scale dynamics aren't playing as much of a role. We don't have these really sharp temperature gradients, and you can kind of consider the tropics, which is a place I study the most, to be like this all the time. It's difficult in terms of predictability because we don't have these clear lines of convergence and frontal systems. And so this is an example that may be close to some of you, where there was derecho, a very intense downward motion of air that created really intense winds at the surface in June of 2012. And actually, most numerical weather prediction models gave no indication that any precipitation would even develop, let alone a significant severe weather event. So there are significant operational challenges that come about when we think about forecasting deep convection. And a lot of that has to do with the fact that climate and weather forecasting models many of them are not convection permitting, and they struggle to represent characteristics of larger convective systems that form severe weather events or heavy precipitation events. And we call those mesoscale convective systems. So MCSs are responsible for producing the heaviest convective rainfall across the world. And so what our research does is we try and distinguish environmental conditions that permit the organization of convective cells into MCS structures. So how do we get from an isolated cumulonimbus cloud to a more organized convective structure? And so in the US, I just kind of mentioned and alluded to the fact that there are certain dynamics here that have to do with like warm and cold air banging up against one another. And we call that wind shear, that are more influential for organization of convective systems than in other parts of the world, like in the deep tropics, where we really don't have that, but we have convection almost every day. Or, that's an overstatement. But so in the tropics, subtle local perturbations to moisture and temperature really matter quite significantly. And so that's what my group tries to study, is like what are these local perturbations that really do matter for the upscale growth of convection from isolated convective systems to larger, really intense convective systems. And so this is just a quick example of something that we're doing in my group. So we're like tracking individual MCSs, as I mentioned before, and compositing satellite-derived profiles of temperature and moisture. So like here on the top, this is from my student Sayali, who she's taken data from the NASA atmospheric infrared sounder, and she's composited temperature and moisture ahead of the MCS genesis at time 0 here. So an increase in temperature in the lower atmosphere, an increase in moisture many, many hours before that actually lofts. And we think that that has a lot to do with the fact that at this point, you have a developing convective system that's heavily in training. And so if you don't have enough moisture, or heavily mixing, if you don't have enough moisture in the lower atmosphere, it's not going to continue to grow. So things like this we try and do to distinguish certain environments. Or here she's actually taken a really awesome approach to this is like where the MCS centroid would be. This is a bunch of it's basically a column integrated moisture. And you can see that if we composite events in their growth phase, that actually in the direction they're propagating, which is in this case, all the data is rotated and averaged so that the MCS centroid is moving north in this example, there's actually enhanced moisture ahead of the convection, which is kind of cool. So it's not just in space or not just in time that we're thinking about these perturbations and what leads to the larger convective systems developing, but also in space, like what perturbations in space might occur that might allow the growth and maturation of convective systems. Okay, so a little bit closer to home, this is just a radar example from the other day on April 15th, on Monday, where we had some isolated and some larger mesoscale convective system type convection. And another approach that my lab group is taking is generally just trying to look at the environments, not just of MCSs before they grow, but comparing environments in which we only see isolated deep convection to environments that we see MCSs. And so this is just a quick example in blue. This is for the southeastern US. Actually in black, this is for all of the continental US. So in blue, actually, in the southeastern US, it appears that so the solid line is for the larger mesoscale convective systems, and the dashed line is for the isolated deep convective systems. So like not connected to other convective cores, just sort of isolated in its own world, as opposed to these being more connected to and aggregating and probably dumping a lot of precipitation. And so in general, this is the total integrated moisture on the x-axis here. It seems as though, or we have evidence that mesoscale convective systems in the mid-Atlantic, the Southeast, generally are favoring higher moisture environments. So moisture might be quite important to their upscale growth, but that's not necessarily true in other parts of the US. So just a little bit about what we do. Okay, I think I'm going to come back to this potentially at the end. But this is just an illustration of how deep convection across the United States might be changing. So actually, the number of thunderstorm days there's evidence that it will increase in the eastern US and decrease in the central Great Plains. And how do we know this? Well, we do dynamical downscaling or making a higher resolution model output from climate models in certain regions of interest to try and represent convective system processes in greater detail, and then evaluate how changes to the climate system might affect this. Okay, so the next approach that we take in our work is studying changing cloud characteristics, which actually create significant spread among climate models in their warming responses to greenhouse gases. So this is motivated by wanting to constrain our uncertainty in the magnitude of global warming from anthropogenic greenhouse gas emissions, which ranges more than we would like, even though it's absolutely warming, and it's absolutely warming at least by 2.5 degrees Celsius or so by 2100. Those things are known, but the range over which the warming can occur depends actually a lot on how the cloud landscape changes. So how clouds change are what we refer to as cloud feedbacks. And so I've been studying in my lab group tropical cloud feedbacks. So I'll just start by saying that different atmospheric and oceanic circulations can create different cloud types. So for instance, in the mid-latitudes, we have air that's mostly rising along fronts, and this is depicting a warm front, but it doesn't necessarily have to be, it can be there are other types of fronts. But in general, we see more of like stratiform type precipitation and frontal lifting. In the tropics, we have air that's rising in a very warm, moist band called the intertropical convergence zone. You can actually kind of see, like, this is the US West Coast, this is Mexico. This is the East Pacific. You can see this narrow band of really intense deep convection. That's what's sort of depicted here. And then there's a convergence that creates, the deep convection, warm, moist air, a lot of solar insolation. And then there's a return circulation or a downward circulation in what we call the subtropics. And so here on the imagery, you can see that they're actually pretty extensive low clouds below this larger scale subsiding air. So just sort of to orient and how there can be different cloud landscapes in different parts of the world. So two of the most robust cloud feedbacks that climate models are showing is that cloud tops are rising and tropical low clouds are reducing. And those are contributing most to the total cloud feedback parameter and the uncertainty in climate change. So let me describe a little bit. What do I mean by low cloud amount feedback? Okay, so if we're in the present day and we have low clouds over the ocean, low clouds are extensive and pretty reflective. So if we warm the climate, and climate models are generally predicting that these low clouds are going away, we're going to get more sunlight reaching the Earth's surface, and the Earth's surface is a lot less reflective than the white clouds. So that ends up as a positive feedback on the climate system. You warm the climate by greenhouse gas forcing, you get rid of low clouds, that further amplifies the warming because you're increasing your absorption of solar insolation at the surface. Okay, the high cloud altitude feedback is a little bit more complicated, but I thought you guys might be interested. So here I am going to try and present it. So in present climate, assume that clouds, they don't, but assume that they're going to increase in height. What would that do to the climate? Well, clouds emit radiation, and anything emits radiation according to its temperature. So if you increase the cloud altitude, it's colder up there. So your cloud top is colder. So you're emitting less infrared energy or long wave energy from the cloud top. And so what that would do is that would mean that with respect to a cloud-free surface, you end up getting more infrared energy re-emitted back towards the surface, and that would make our surface warmer than it would be with lower cloud altitudes. Okay. Let's consider another scenario. We warm the climate, but high cloud altitude doesn't change. Well, in this case, we're warming the entire troposphere. So you actually end up, if you don't change the cloud altitude, you have a warmer cloud top. Now, the cloud tops warm again proportionally to their temperature to the fourth power. So you have warmer cloud tops, you have more emission from the cloud top. So what happens is you also have more emission from the surface because greenhouse gases are warming the entire column. They're not just warming up here, they're warming the surface, they're warming everywhere. So you have greater greenhouse gas emission from the hotter surface, but that actually is communicated to space because you would have a warmer cloud top if clouds didn't rise. So there would be no feedback there. But actually, clouds are rising. The cloud altitude is increasing. So what happens is this impedes Earth's ability to radiate additional heat from greenhouse gases warming the atmosphere. And so what you have is you have the same amount of energy going out at cloud top because actually the temperature remains nearly constant. That's sort of a fun physical fact, is that the clouds are increasing, but their emission temperatures are staying roughly the same. So the same amount is going out from the cloud tops, but more is coming from the surface because we've heated the surface. And so the re-emission of infrared energy from the clouds and the atmosphere back to the surface is going to be greater because we have less going out. So that actually acts as a positive feedback. Okay, why do we care about clouds? Why am I talking about this? Well, clouds actually cool the planet 5 times more than the planetary heating by increased greenhouse gases. To give you some sense of clouds really matter for the Earth's energy balance. Somewhere on the order of 20 watts per meter squared of cooling, 4 watts per meter squared of greenhouse gas forcing. So this is pretty substantial. So even subtle changes to clouds can strongly amplify or dampen that warming. And you can see that the Earth is pretty cloudy, so it's no surprise that they're imparting a significant influence. So most climate models simulate a positive net cloud feedback. That's shown here. This is cloud feedback magnitude in watts per meter squared per degree Celsius. And the total cloud feedback, this is the range among all models, but most predict, there are a couple of outliers, but most predict that there's a positive feedback. So you increase greenhouse gases and you warm the planet, that is then amplified by changes to the clouds. But climate models differ in the strength of the varying feedback components. So these are the two feedbacks we just talked about, the low cloud amount and the high altitude amount. And you can see that models vary non-trivially in how they represent these feedbacks and some of the other cloud feedbacks that I don't have time to talk about. And really, clouds are the dominant driver of uncertainty and estimates of the magnitude of global warming among climate models. So that's sort of what I'm showing here. This is the increase in temperatures predicted out to 2100. Highlighted, these are the range of models in the gray, but highlighted here are two ensemble members, one that predicts less warming and one that predicts more warming. And the one that predicts more warming has a higher net cloud feedback, and the one that predicts less warming has a lower or negative cloud feedback. And so if we were to scatter on average the net cloud feedback that's produced from the models and what we call the climate sensitivity, or the overall warming of the climate, to traditionally it's defined as like a doubling of carbon dioxide, you can see that there's a relationship between, if you have a more positive net cloud feedback, then you're going to have a higher climate sensitivity. So this really is driving a lot of the spread in the estimates of the magnitude of global warming. So in my lab group, our research is trying to quantify the largest sources of uncertainty in the net cloud feedback and climate sensitivity, therefore, among models. And we do have aims to observationally constrain the spread as appropriate, which I don't have time to get into. But anyway, so low clouds are historically, the last decade or so, a lot of studies have suggested that low clouds are known to contribute greatly to this spread. But actually, one of my master's students has done some really nice work recently, and she's been looking at high clouds. And she's been looking at the relationship between climate sensitivity, or the amount of warming expected with a doubling of carbon dioxide, and high cloud feedbacks. So this is for like thin high clouds, the change in amount, the change in altitude, the change in optical depth of the clouds. And all of these quantities are, these are the correlation coefficients in the bottom. They're significantly correlated to climate sensitivity. So it's not just the low clouds that are imparting a significant influence on the spread and estimates of warming in the future. It's also these thin high clouds in particular. Okay, sort of tying everything together and coming to a close. So, deep convection and cloud feedbacks are all pretty interconnected. I mean, especially in the tropics. And so improving our representation of deep convection in climate models is really another way to reduce uncertainty in estimates of cloud feedbacks and climate sensitivity. So these are sort of how the themes come together in my lab group, where we're trying to think about ways of studying deep convection and improving their representation in climate models and weather prediction models. But we're also trying to think about cloud feedbacks and climate sensitivity and how models differ in the way that they represent clouds and cloud feedbacks. And a lot of that may have to do with the way that they have diversity in representing deep convection. And so that's kind of, those are the intersections I sort of work at. And we've done some work specifically at that intersection recently that you're welcome to go check out. So in summary, our goal in our lab group is to improve our understanding of thunderstorms and clouds, to improve predictions of the magnitude of global warming and associated increases in extreme weather events, right? If we warm the planet more, we're probably going to have more intense extremes. So that all kind of goes hand in hand. And then our approach is really just studying which environments support the growth and maturation of thunderstorms, or the decay of thunderstorms, to model these events more realistically, and studying the changes in cloud characteristics and the physical basis for those changes. So if you'd love to learn more about us, please feel free to contact me. I wouldn't say my website is particularly up to date, but you're welcome to go. I'm really, again, appreciative of the invitation to be here, and I'd be happy to take any questions.
Thank you so much, Dr. Schiro, for that riveting talk. I'm going to give clouds a lot more credit now. And I will still wear my SPF when I'm at the beach this summer. So yeah, let's hop into some questions. We're going to start with one pre-submitted question, then we'll take one from the Q&A. So the first question I'll ask, which was pre-submitted, what does the climate change data show about what geographic areas of the US and world will experience increased or decreased rainfall? And over what period of time will these changes occur?
Yeah. Okay. So a few slides ago, I actually did show a slide that was illustrating, for instance, that changes in convective events in the east are generally increasing. And then actually in the central Great Plains, convective activity isn't necessarily increasing and might be decreasing. So that's sort of closer to home to give some sense. And then, so I guess I touched on that a little bit, but then in terms of more geographic broad scope, this is the change in annual maximum daily precipitation. So this is the total change across the globe on average, change per degree of Celsius of global warming. So you see actually that like most of the globe, the annual maximum daily precipitation, which is kind of some way of quantifying rainfall extremes, is increasing. And a lot of that has to do with the fact that if you, it's this basic physical relationship between temperature and moisture. So if you increase the temperature, the moisture content of the atmosphere will increase by about 7% per degree Celsius of warming. And so we call that, that's sort of what's plotted in the middle here. That's the thermodynamic, or the moisture temperature contribution, to the change in precipitation. So that's fairly uniform in most places. What actually changes the pattern in different places is things like changes to the atmospheric circulation. So the circulation intensifying or weakening in certain regions can create zones of drying or wettening, and that contributes overall to these patterns. So I'll say that this is the maximum daily precipitation. So these are more like spatial maps of what extremes might look like, which generally they're becoming more intense and they're increasing, like rain rates are increasing because moisture content in the atmosphere is increasing. But if we take an average, like annual mean precipitation change, there are certain regions that are getting wetter and drier. So like extremes are generally increasing in terms of how intense precipitation is occurring in most land regions and in most places. But then there are subtle regional differences in various places, and that this is just a mean. This isn't extremes. So like, for instance, in the Amazon, models actually don't agree a ton, but generally suggests that the Amazon is getting drier. In the southwestern United States, where exactly this line is, where there's an increase in precipitation or a decrease in precipitation, sort of depends on the climate models, but there's generally a drying in the southwestern United States. But in general, there's a wet get wetter and dry get drier pattern. So like the wetter regions of the world get wetter and the drier regions of the world are getting drier. And that pattern just amplifies with additional greenhouse gas forcing. So like if you simulate the changes at 1.5 degrees Celsius warming versus 4 degrees Celsius warming, you see that those patterns sort of heat up. So I hope that answers that question. I'm glad I happened to randomly have a couple of slides.
And then one from the audience has to do with the land cover type. And does, for an example, does a vegetated surface versus impervious surface affect the intensity of storms?
That's such a great question. Yes, so that's actually, the jury's still out about exactly how different types of land characteristics could affect convective systems. Some studies suggest that drier soils and drier land conditions, because it can heat up faster, you get surface convergence, you could have potentially more intense convection. Some studies suggest that. Some studies suggest that convection preferentially occurs over moister soils. And some suggest that actually it's the gradient. It's how strong of a gradient there is between a moist soil and a dry soil, and that can induce a circulation and affect the convection. So that's often been studied in terms of convective initiation. This is something I'm starting to play around with in my lab. I actually have a postdoc, Laura Pacini, who is doing some simulations where she modifies land surface conditions, and she's been looking specifically at the effect of soil moisture, but there's also vegetation and complex vegetation dynamics to consider. So it really depends on what type of convective characteristics you're interested in studying, what phase of the convective life cycle, whether you're looking at the individual storm scale or on like a broader spatial scale. And then, of course, land use and land cover change can influence convection.
Amazing. Well, thank you all. Thank you, Dr. Schiro, for just enlightening us with just how our atmosphere is and what climate change is trending and projected to go. I highly encourage everyone to definitely reach out. We couldn't get to all your questions, but definitely reach out, go visit the website, see the great work that Dr. Schiro and the students at UVA are doing, because it is truly incredible, and you got to see bits and pieces of it today. So go check it out, reach out if you have any questions. And lastly, thank you all for joining us for our third installment of Through the Lens, and hope you enjoyed and have a great rest of your day. Thank you, Dr. Schiro, again. Bye, everyone.